Hi, my name is Julia Silge and I am a data scientist and software engineer at our studio. And today in this video, we're going to use this week's Tidy Tuesday dataset about astronauts and their missions, the missions that they're on. And we're going to build a model to predict the duration of their mission. We're going to use bootstrap aggregating and the baguette package, which is part of the tidymodels ecosystem, to explore what we can learn about what affects how long astronauts are on their missions.
All right, let's explore some astronaut data. So this week's Tidy Tuesday dataset is about the missions of astronauts. And let's take a look at what we have here. So this data set is one astronaut per mission, per row. So you can see, for example, we have duplicates per person and duplicates per mission, and so it's like per person per mission per row, and we have a lot of really great information about these missions, including like whether there was an extra vehicular, like whether people went outside of the spaceship, how many hours were on the mission, how many hours that person had been in space total. There are these three kinds of information on the spacecraft, like what did they go up in, what were they in orbit in, and then when they descend in. You can see that for these early, so here we're back in 1966, and they're it's the same, you know, they went up and down in the same thing. But then if we go to much more recent missions, people would go up in one shuttle and then, for example, be up in the like the ISS or Mir, one of the space stations that's permanently in orbit around the Earth, and then return in a different kind of space craft. So these STS, these are all the U.S. space shuttles here, and so we have lots of really interesting information. And then there's mission titles, the year of the mission, the occupation of the person, and then some different information on the person. So what we're going to do in this video, in this screencast, is we are going to build a model for for this hours of the mission based on this other information. So based on the person and the mission, how long, well, what can we build a model to predict how long the mission, that person was on that mission based on information about the person and the mission. So we're going to build a predictive model given everything we have in this data set to predict this number. So this will be a regression model, and we are going to use we're going to use bagging here, so bootstrap aggregating for the kind of model that we're going to do. So let's get started on that. Before we get started on the modeling, let's just explore a little bit that variable. So let's, for example, I know from some of the other beautiful visualizations that I've seen around from what people have done, that the time that people spend in space has been changing with time. So I want to make a visualization so that I can see that and start to understand a little bit about the data that I have. So I'm gonna say, let's see, I'm gonna make a factor out of the year. So let's say year of mission. Let's do floor. So that's floor. So like if you take 1983 and divide by 10 like that, yeah, so you'll get like 1980, and then if we multiply that by 10, we'll get the decades, like so. So that will give us, 1980. And then let's turn that into a factor. Year of mission equals factor year of mission. And let us make just a little bit of a plot here before we get started. So let's put year of mission on the x-axis, hours of mission on the y-axis, and then let's make a box plot here. And let's see what that looks like. Whoops. All right. Okay, so let's start making this box plot a little bit better. First of all, let's put that scale on the y, let's scale that y-axis, but the log here. That's pretty good. We don't need those labels, and let's call this duration of mission in hours. And then I think I will prefer to do make these colored for clarity here, and then that means I don't need the legend anymore. That will make, and let's make that nice and transparent and a little bit thicker. Here we go. So what we have here is, this is what we want to predict, this thing on the y-axis, how long we're on a per person, per mission basis, how long were people in space, how long were astronauts in space. And we can see that over time, the median time in space is going up. From the 1960s through the 2010s. You can see that it, like back in the 60s, it was like Apollo missions and, the first mission sent by the USSR. And here in the 2010s, we have people going up on the to the space stations and spending, like, this is hours, right? So this is on the order of a day down here, and this is on the order, we go through weeks to months. So this is a big shift. And here this is on a log scale, and I think I am actually going to model this on the log scale and be able to understand what in the data set that we have here is related to this change from days to weeks to months. We definitely can see that time impacts it, but what else in this data set impacts it, and can we learn something about that and model it? We're going to use the approach of bootstrap aggregating. So, we've got this. We could of course do tons more exploratory data analysis, but let's move on forward here. So let's build the data set that we're going to use. Let me just put the names here so I've got them. So we are going to take, I'm going to take the name and the mission title, and these are things I won't use to model, but if I wanted to have them later as identifiers, they'll be there for me. So we definitely need hours mission, because that's the thing we're going to predict. That's our outcome. Let's take that military civilian category that says whether they are a military or civilian. Let's take occupation. That was the thing. Are they a pilot? Are they some kind of specialist? What was their role on the mission? We definitely need year of mission. We can see that has a super strong effect on the duration of the mission. And then let's take that. We remember we have these three aspects of what kind of spacecraft people were in. We could try to model all three. For this screencast, I'm only going to take the middle one. So, if they were on the space shuttle, it'll be that. If they were, if they went to the space station, that will be what gets there. And then if they were, back in the back in the olden times, it'll be like, you know, one of these Russian spacecraft or the USSR spacecraft or Apollo or Gemini or whatever. So I'm just going to take in orbit, so just one of the 3 spacecraft. I'm going to filter out only missions that actually went to space, because I am going to take the log here, hours mission. So notice this is my outcome, and I am going to transform my outcome here in my before I start working, before I load tidymodels and start working with my actually modeling toolkit, because this is something that is not that doesn't depend on you know, like the predictors. It is something that I just know I'm going to take the log. It's not something that depends, you know, on that input data. So I'm not going to put it as a step in a recipe. I'm just going to take the log before I get started, and that is going to solve me some headache going forward. And I don't think there's any NAs in this data, but I'll just put that there to be safe. So let's call this astronauts DF, and this is the data set that I'm going to use for modeling. So let's get started with some modeling. I'm going to load tidymodels like this. And then the first thing that I'm going to do is I'm going to split my data into testing and training sets. So let's make the strata the outcome. So since this is a regression model where this is a continuous variable, what it will do is it will make bins, and it will try to make sure that when we do this sampling, it will do stratified sampling, so it's about equal in the bins that it makes. So let's call this astro split, and then I am going to make astro train, and so this will be the training data, and astro test, and this will be the testing data, like so. So I've now split my data into training data and testing data. And so this hours mission is the thing that I am going to predict. And notice we've got, you know, we go from very low numbers. Remember, this is now on the log scale, very low numbers to very high numbers. Okay, so the next thing I'm going to do here is some data preprocessing. I am going to use the recipes package for this. The recipes package is a package for data preprocessing for feature engineering. And the first thing I do is I specify my recipe. I initialize it, and I say the thing I'm going to do is I'm going to predict the hours of mission with everything else in my data. I say, what is my data? My data is this training data here. And then I start to add steps to it, like steps to a recipe. The first thing I'm going to do is I'm going to update the role, because remember, I've got name and mission title in it, and those are actually not predictors. So I'll I'll say, let's just call those ID, like that. So what this means is those are still in the data, but I do not, those are not predictors, and they are not outcomes. I just am keeping them around in the data for convenience later. Some of these things have a ton of levels, like occupation has quite a lot. And in orbit has quite a lot. Remember, there's a ton of different kinds of spacecraft here. Oh, you know what? In fact, there's so many. Let me just go back to here, because I just want to call all of the spacecraft, for example, all the space shuttles I'm going to say string detect in orbit. For example, let's see. Well, let's say what are the top ones? Astronauts count in orbit sort equals true. All right, so this is a space station. This is a space station. Let's put this kind of spacecraft, and let's call that just Salyut. Apologies to my Russian friends. And then these, let's call STS, and I think that's probably good enough. Everything else, let's just leave true in orbit, like that. Okay, there we go. So that helps some, but we still have a lot of different kind of spacecraft. So we're going to use step other like this, and let's say occupation in orbit, and let's call it other equals other, because these are capitalized. I mean, it doesn't really matter. Doesn't matter. And then we're going to use step dummy, which means we're going to convert columns that are factors to indicator or dummy variables, meaning we're going to have, instead of a column that says occupation with pilot, commander, pilot, this also has different capitalizations. So let's add right here occupation string to lower occupation. All right, one more time. Data cleaning, it'll getcha. Okay, and let's say all nominal, but let's subtract the ones that have the role ID here, because we don't want to turn these into dummy variables. That would be we just want to leave those as they are. So what step dummy does is, instead of having a column that says occupation with all these different values in it, like commander, pilot, instead we'll have columns that have zeros and ones in them, and the column titles are things like occupation underscore pilot. So let me show you how that works. So we have the recipe now. The recipe has been specified, but nothing has been estimated or trained or executed yet. So the way we do that is by prepping it. Now these things have happened. They have collapsed the factor levels, and the dummy variables have been created. It looks like, how many did this make? So prep means estimate it. Juice means get the data back out. How many? So for occupation right now we have 1, 2, 3, 4, 5, and we have 3 options for in orbit. That is not enough. I can have more than that. So let's drop the threshold down. Let me remind myself what the default is. So step other, the default is 0.05. So let's drop the default down to the threshold down to 0.01. And let's juice it to get what's out. So prep estimates the numbers, and then juice says, give me the data back out. So now we've got mirror, Salyut, we still don't have the ISS. Let's go down, whoops, one more time. All right, so now we've got space tourist, delightful, and now we have, all right, we still don't, because the ISS is the default level. Okay, I think this is good though. So ISS is the default level, and then Mir, Salyut, the space shuttle, other, pilot. I think that's good. Let's leave this like this. I think I like that. That's a good option. Okay, so that's our recipe. So this is our data pre-processing, and now we have so year of mission, and these things are the things we're going to use to predict the hours of mission on the log scale. So the kind of model that we're going to use is we're going to use a bagging model. So bagging models are available in tidymodels through the baguette package, which I love the name of. And so a bagging model is like this, the other word for that is bootstrap aggregating. So it's an ensembling method, or it's like a model averaging method. So the benefits of this, why we use this, is that it compared to using just one model, it improves accuracy and stability, and it reduces overfitting and variance, which that all sounds great, right? So what will happen is we will take this data set that we see right here, and when we do this bagging method, we will we'll create new bootstrap training sets of this data set that we see right here. So we'll create new resamples. So resamples with replacement. So we'll say, okay, I need 954. And then we'll say I need 954 again, and we'll draw with replacement from that that data set, and we'll fit a model to each one of the bootstrap resamples, and then we will combine by averaging the input. So because this is a regression model, we'll combine by averaging. With a classification model, I think you combine by voting. So let's start, and let's make a workflow. Let's add our recipe to it here, and let's call this our Astro workflow, like this, like so. So let's look at the workflow right now. Notice that it has recipe steps, but it does not have a model yet. We are going to now make our models. So we're gonna use a bagged tree model. So we are going to set the engine. The engine. So the engine here we're going to use is rpart. So this is a decision tree, a bagged decision tree model. And what we say here is times, meaning how many times are we going to do the bootstrap? How many bootstrap training sets are we going to create? How many models are we going to train on them, and then average together to get our prediction? And then here we are training regression models here, which means we average them all together to get the prediction. So let's call this our tree spec, like so. And then we're going to do one other kind of bagged model. We're going to do a bag Mars, and the engine here is Earth. So this is a different kind of bagged model here that we can read about here. So we've got these two different kinds of bagged models here that we can bag together. So we've got our model specs here that work in slightly different ways. And what I'm going to do here is I'm going to take the workflow, and I'm going to add a model to it. First, let's add the tree. And if I just run this, it helps if I define them. So if I add the tree like this, now notice that I have a tree. Before it said models equals none, and now I have it. And right now we're just using the defaults. We could actually tune these if we want for simplicity and time. I'm not going to tune them, but we can actually tune these to get better performance and find out what the right cost, complexity, and whatnot is. But for now, we're just going to use the defaults. And then I can fit this workflow. And what do I fit it to? I fit it to the data, like so. So this will be, let's call this my tree results, like so. Like this, and then let's let's get ready. So this is actually training 25 models. That actually went pretty fast. And let's see what we have here. So this is a bagged cart regression model with 25 members. And it gives us actually the aggregated variable importance score too, which is super convenient and really nice to be able to see. So we can see here that the most important thing is the year of mission. And then these next things are about the spacecraft, the other category, then the space shuttle, then things about what the person did, and then we go on down here. So, but the biggest thing here is the year. So let's see what the Mars model does. So Mars, add the Mars, but other than that, it's the same. And we'll let that one run. So now again, it's like training 25 models, and then it's going to average. When we predict, it's going to average them together. So all 25 models are in this object. So slightly different results. So we've got in the Mars model, the same three things are in the top there in a different order, and the year of mission comes up actually half as important as the shuttle. So we've got different things here. So we've got some slight differences in how this in what we get here. So let's evaluate these models and see what we're doing here. We're already working with resampled data. So let's look at that test data. We're going to just compare these two models and look at what's going on here. So what we can do is let me just show you. If we do a predict, let's look at the tree first. Predict tree on the test data like this. So if we do this, it just gives us a prediction. And remember, what it's doing is it's averaging the 25, in this case, decision tree models for the test data. And we can just bind that onto the test data, the test set here. And since we're going to have two predictions, so let's rename that. Let's call it predict tree equals predict. And then let's do the same thing for the Mars model. Mars. And let's call this our test results, like so. So we've got our test results. So we've got now these two different predictions, each of which have been created using bootstrap aggregation of different kinds of models. And we can find metrics for them. So if we just want like default metrics, we can use the metrics function from Yardstick. So the first thing we pass in after we the pipe is the truth. And then what we want to, then our prediction. So here we see the RMSE, the R squared, and then the mean, mean absolute error. So this is in the same units as the original data, which in our case is the log of the hours, which is, maybe not awesome, but and interpretable, but maybe we could get that back out. Okay, so that's I guess I've seen worse, but that's but what we're trying to do here is understand a little bit. So it looks like, okay, so in terms looks like the so R squared, so RMSE is lower, R squared is higher, MAE is lower. So it looks like the Mars model is a little bit better here. So So, but they're not hugely different from each other. But the Mars model is a little bit better with, at least with these defaults that we used. So we can that's our model performance. You know, we can estimate our model performance this way. We also can use these models to understand the kinds of predictions that our bagged model is making. So let's make some new astronauts. So let's use the function crossing from tidyr and make some new astronauts here. Let's in orbit. So let's say C ISS. So that's the International Space Station. This is the Space Shuttle. This is the Russian Space Station, and other. I think other actually was lowercase. Let's military, civilian. Let's make them all civilians. Occupation. Let's see. Let's look at that Mars model. Other, sure. Other. We could make them space tourists. Okay, and then let's make the year of mission. Let's say 1960 to 2020 by 10, like that. Let's make sure that's right. Yeah. Okay. And is that right? New astronauts. Yeah, okay, so what crossing does is give you every combination of those, which is pretty nice. And then let's, you know what, we're about to make a plot here with these new astronauts data, and I don't want to put things on here that didn't actually exist, because that's kind of the point of what we're doing here, is understanding how did the duration of missions change over time, and so I don't want to, for example, put the ISS on the plot when it didn't exist. So let's do this with knots. So in orbit is equal to ISS, and the year of mission is less than I'm pretty sure it's about 2000. Let's do mirror. I'm just going to paste this. Mirror, I think, was about 10 years earlier. And then let's do the space shuttle. The space shuttle started around 1980, and then it ended I think around 2010, like so. Okay, and then what we're going to do is predict, like if we do the tree. Oh yeah, we just have to put in so this model is expecting name and mission title, even though they're not used in the model. The model that we created is expecting them as IDs. Okay, so here would be predictions here for these things, these hypothetical new astronauts that we've made. Let's say new astronauts, bind calls, and then we're going to put this in there. Maybe we can change to the Mars one too and see what it does. And then what we're going to do is let's put the year of mission on the x-axis. Let's put the prediction on the y-axis, and then let's make color in orbit. Like so. And let's make a line. Let's make a point here. Let's see what that does. All right, let's just change the order. Fact in order like that. Oops, I have to do it all. Let's change the labs. So we don't need a label on the x-axis. We don't need a label on the color. And let's call this Y. So this is duration of mission in hours, let's say predicted on log scale, like that. So let's look at this. So which one is this? This is the tree model. Okay, so what the tree model is saying here, okay, so in the, so we see this change from low to high over time. We see that the space stations are up here on the order of months. The space shuttle is here on the order of like days to weeks, which is in fact what they did. And this other is this grab bag, right? And it's changed over time. So what bagged tree models, or bagging in general, is able to do is able to average over the sort of overfit models of the trees and able to get like these kind of results that make sense. Let's see what happens with the Mars model. Oh, interesting. That does look pretty nice. So the Mars model puts the two space stations really close together, and just right next to each other, and then puts other and the space shuttle very close together as well. Here in this this is down here hours. This is days to weeks. This is months up here. So what the Mars model has done is been able to average over these different categories to be able to find this. So this shows what nice results we can get from this kind of bootstrap aggregating in situations where we have nonlinear effects from, say, time, in this case, time, and these different kinds of categorical predictors, and be able to understand something about what the impacts are.
All right, we did it. We used bootstrap aggregating of a decision tree model and a Mars model with splines and knots and things to predict the duration of astronauts' missions and to understand what affects it, like what year the mission was in and what spacecraft they were on. So bootstrap aggregating can help with overfitting and reduce variance and increase stability, and is a really great toolkit to have a really great option to have in your toolkit. So I hope this was helpful, and I will see you next time.